In molecular spectra, till now we have discussed mainly the rotational spectra, the rotational vibrational spectra, and the Raman spectra. Okay. Now we are going to start a new chapter in molecular spectra, and that is actually a very important chapter which is called electronic spectra. In fact, you will see that among all these molecular spectra, this electronic spectra is most complex. Why it is most complex? We will see the cause. Okay. Actually, this is my first lecture on this electronic spectra, and so this is just an introduction, or you may say that this is just we will see just the salient features of the molecular electronic spectra in this lecture. So this lecture is just an introduction and will contain no calculation. We will only see some of the basic features or some of the outlines regarding this electronic spectra. In fact, in my most of the videos, in comment section, so many viewers ask me to give the PDF form of the lectures. But I would like to say you that in fact all of my videos contain each and everything written, so there is no separate need for PDF form of these lectures. If you want to note down each and everything, there will be a good notes for your examination. So you can pause the video, note down each and every step. You will find already the lecture is in PDF form. So keeping this fact or this demand in mind, in this lecture I have noted down each and every fact in detail. So as there will be no calculation since it is just an introduction, so I have written every fact in detail in this lecture. So if you want to write down these facts, you can pause the video, or during watching the video you can also write it. So take your notebook and pen and write down each and every step and then revise it. Okay. So there is no extra need of a PDF form of these videos, as some of the people wants like that. Okay. So as I have told you that this chapter is regarding the electronic spectra, and you know electronic spectra or any molecular spectra or any atomic spectra always arise due to some transition. When you talk about the atomic spectra, the atomic transition takes place between two energy levels, and if the transition takes place from lower level to higher level, then energy is required, energy is absorbed, and you get the absorption spectra. And when that transition takes place from higher energy level to lower energy level, then emission spectra arise, because in that process energy is radiated in the form of electromagnetic radiation. Okay. Now as a electronic spectra is a molecular spectra, so this spectra arise due to electronic transition between two electronic energy levels. Let us consider that this is one energy level, this is another electronic energy level, and if you say that this L is the lower energy level and this U is the upper energy level. Okay. So in this condition, if our molecule is in the lower energy level, then energy is supplied to the molecule in the form of electromagnetic radiation, And when you actually supply the appropriate amount of energy, that is the energy equal to the difference of these two energy levels, the molecular transition takes place from this L level to this U level. Okay, and energy gets absorbed, and you get actually the absorption molecular spectra. Okay, and if the molecule is already in the upper energy level and it transits from this upper energy level to the lower energy level, then energy is actually emitted and you get the emission spectra. Okay, but remember, if you want to get the electronic spectra, this energy level is actually the electronic energy level. So you can say that an electronic spectra is obtained due to the molecular transition between two electronic energy levels of the molecule. Okay. In fact, these electronic energy levels are far separated, and so more energy is needed for such transition. Or you can say that if we use the electromagnetic radiation for exciting the molecule, then the amount of energy of the quantum of radiation should be very large. Okay. But remember one thing, when this electronic transition takes place, at the same time there is a change in the vibrational energy of the molecule and also the rotational energy of the molecule. So whenever electronic transition is suffered by the molecule, definitely there will be a vibrational change and a rotational change of the energy at the same time. Okay, and that's why this is the reason that the electronic spectra is the most complex spectra. Okay, because whenever you will talk about this electronic spectra, you have to consider how much vibrational energy changes, how much rotational energy changes. So the vibrational term and the rotational term are also found while dealing with the electronic spectra along with the electronic term. And that's why we simply say that the electronic spectra is the most complex spectra among all the molecular spectra. Okay. And as I have told you that when our molecule is in some lower energy level, that is the electron of the molecule is in the molecular orbital which is completely occupied, and your aim is to transfer that electron to some higher orbital which is either partially filled or completely empty. Then energy will be needed from outside. We actually supply the energy in the form of electromagnetic radiation or the quanta of radiation. Okay, and after absorption of the electromagnetic radiation, the molecular transition takes place from lower level to higher level, and we get actually the absorption electronic spectra in this condition. Okay. Now see, as I have told you that energy is supplied in the form of electromagnetic radiation. But the question arises that when our molecule in the lower energy level is transit to the upper energy level after getting energy from the electromagnetic radiation, what will be the appropriate radiation for this purpose? Actually, it is seen that when molecular transition takes place between two electronic energy levels, then either we need the visible electromagnetic radiation or the ultraviolet electromagnetic radiation. So you can say that this electronic spectra lies in the visible region and the ultraviolet region of the electromagnetic spectrum, because the energy of the photon of visible radiation and the ultraviolet radiation has the appropriate amount of energy which is just equal to the difference of the two electronic energy level of a molecule. Okay. Now, as I have told you just now that in case of this electronic transition, there is also a change in the rotational energy and the vibrational energy of the molecule. So actually, a molecule in each electronic level can execute the vibrational and the rotational motions too. Okay, and that's why when you talk about the total energy of the molecule, that consists of three energies or three terms. So if you say that this E total represents the total energy of the molecule in an stable electronic energy level, then that energy is equal to EE plus EV plus ER. Actually here this EE represents the electronic energy, E subscript represents the word electronic, EV represents the vibrational energy, and ER represents the rotational energy. Okay, and as I have told you just now that when electronic transition will take place, then actually this vibrational energy and the rotational energy also gets changed. Okay, and so I have mentioned it here that electronic transitions are accompanied by the change in vibrational and rotational energy levels. Okay. Now it is seen that the vibrational transitions appear as the coarse or gross. It means due to this vibrational energy change, we get a band spectra. Okay. Or you can say that we get the discrete spectral lines. But when the rotational transition takes place, that gives actually the fine structure. So you can say that electronic spectra consists of both coarse or gross structure and also the fine structure. Actually in the forthcoming lecture we will see separately that the vibronic coarse structure of electronic spectra and the rotational fine structure of electronic spectra. We will see these two spectra in separate sections in separate lectures. Okay. So conclusion is that during this electronic transition, vibrational and rotational spectra are also obtained. Actually the vibrational spectra is a coarse or gross has coarse or gross structure, while the rotational transition gives rise to the fine structure of this electronic spectra. Okay. Now you have seen that the diatomic molecule is the best candidate to produce the molecular spectra. In the previous lectures, we have always considered diatomic molecule producing the different type of spectra like rotational spectra, or you can say pure rotational spectra, and rotational vibrational spectra, the Raman spectra. Although the polyatomic molecules also give rise them, but we have discussed in detail the molecular spectra produced by the diatomic molecules. And you know diatomic molecules are actually of two types. First one is called non-polar molecule, which means the molecule which has not a permanent dipole moment. Or you can also say such a molecule homonuclear molecule. Homonuclear molecule, it means the two atoms are identical like hydrogen H2, the two atoms are identical like nitrogen N2, like O2. These are homonuclear molecules. And these homonuclear molecules has not a permanent dipole moment. Actually, it has instantaneous dipole moment, but the vector sum of the dipole momenta is equal to 0. So we simply say that the homonuclear molecules have not permanent dipole moment. On the other hand, in case of the heteronuclear molecules like HCl, like HF, these have actually permanent dipole moment. And you have seen earlier that the rotational spectra and the rotational vibrational spectra are obtained only from the heteronuclear molecules, that is the molecules which have permanent dipole moment. Okay, and these homonuclear molecules do not give rise to the rotational molecular spectra and the rotational vibrational uh, molecular spectra. Although you have seen that Raman spectra is also obtained from these homonuclear molecules which have not permanent dipole moment. Okay, just like Raman spectra, in fact, this homonuclear molecule also give rise to the electronic spectra. It means you can say that electronic spectra are obtained both from the homonuclear molecule which have not a permanent dipole moment and the heteronuclear molecule which have permanent dipole moment. So in simple way you can say that all diatomic molecules, that is both homonuclear and heteronuclear, exhibit electronic spectra. This is a very remarkable fact, you know. As a rotational spectra you have seen are obtained only from the heteronuclear molecules having permanent dipole moment. Rotational vibrational spectra are also obtained from the heteronuclear molecules having permanent dipole moment, and both of these spectra are not obtained from the homonuclear molecules which have not permanent dipole moment. But like Raman spectra, this electronic spectra is obtained from all diatomic molecules, that may be a homonuclear molecule like H2N2O2, or that may be a heteronuclear molecule like HCl, HF, etc. Okay, but what's the reason behind it? In fact, in case of these homonuclear molecules have not permanent dipole moment, but this homonuclear molecule have also instantaneous dipole moment, and during the electronic transition there is a redistribution of charge. When electronic transition takes place from between two electronic energy levels, actually in that condition there is a redistribution of electronic charge, and this redistribution of electronic charge gives the electronic spectra. So I have mentioned it here. You can see that homonuclear molecules like H2, N2, O2, etc. have no permanent dipole moment. So they do not give rise to rotational and vibrational spectra. Okay? But these molecules give rise to electronic spectra. Mark this thing. This is very important fact. Why these molecules give rise to electronic spectra? The reason behind this is what? This is due to changes in the instantaneous dipole moment during the redistribution of electronic charge which accompanies the electronic transition. Okay? So in nutshell you can say that all diatomic molecules, that is both heteronuclear and homonuclear, give rise to electronic spectra. Okay? Now as I have told you that this electronic spectra lies in the a region of visible radiation and ultraviolet radiation. So the wavelength range for this electronic spectra lies between 1000 angstrom to 8000 angstrom. Okay. Now, from the study of these electronic spectra, what informations about the molecule we obtain? This is what are applications of this molecular spectra, that is electronic spectra. Actually, we will see these applications in the forthcoming lectures, but here in the salient feature you have to mention it. So remember, or you should remember it, that from the study of this electronic spectra, we can find a quantitative idea of the different excited electronic states of the molecule and vibrational rotational structure of a spectrum can be used for the calculation of bond distance, force constant, and bond energy, okay, in the ground state and the excited states. So these are the important applications which we actually obtain from the study of electronic spectra. So this was a very brief introduction regarding the electronic spectra, and from the next video we will actually discuss these electronic spectra in very detail. The most important concept of this chapter will be actually the Frank-Condon principle, and that is very important for both the university examinations and the examination like civil services and state public service commission. So Frank-Condon principle will be actually the most important concept of this chapter. Okay.